the fundamental principle of logarithmic differentiation. Welcome, everyone. Today, we are going to explore the fundamental principle of logarithmic differentiation. Let's begin by reviewing some ground you have already covered. In your previous studies of calculus, you have learned how to differentiate functions with a constant exponent, for example, x to the power of n, by using the power rule. Similarly, you have learned how to handle functions with a constant base, such as a to the power of x, by using the exponential rule. However, a challenge arises when we encounter functions where both the base and the exponent are variables. To illustrate this, consider the function y equals x to the power of x in this specific case. The base is x, and the exponent is also x. Because neither the base nor the exponent is a constant, neither the power rule nor the exponential rule can be applied directly to find the derivative. To solve this problem, we use a specialized technique called logarithmic differentiation. The core objective of this method is to utilize the properties of logarithms to transform a complex exponentiation into a simpler product. Once we have converted the expression into a product, we can then differentiate it using the product rule and the chain rule. In the upcoming slides, I will guide you through the systematic step-by-step process of how to actually perform this transformation and calculate the derivative. The step-by-step process. Now that we have established why we need logarithmic differentiation, specifically because the standard power and exponential rules fail when both the base and the exponent are variables, let us walk through the systematic process to solve these types of problems. We are looking at a general function where y equals u of x raised to the power of v of x. To find the derivative, please follow these 4 steps. Step 1 is to take the natural logarithm of both sides of the equation. By doing this, we transform our equation into log y equals log of u of x raised to the power of v of x. In step 2, we apply a fundamental property of logarithms. The power property allows us to move the exponent down as a multiplier. This simplifies our expression to log y equals v of x times log of u of x. This is the most critical part of the process, as it converts a complex exponentiation into a product. Step 3 is where we perform the actual differentiation. We differentiate both sides with respect to x on the left side. Since y is a function of x, we must use the chain rule. Therefore, the derivative of log y is 1 over y times di over dx. On the right side, we have two functions of x multiplied together, v of x and log of u of x, which means we must apply the product rule. The differentiation is structured as follows. 1 over y times di over dx equals v of x times the derivative of log of u of x, plus log of u of x times the derivative of v of x. If we further apply the chain rule to the term log of u of x, the equation becomes 1 over y times di over dx equals v of x times 1 over u of x times u prime of x, plus v prime of x times log of u of x. Finally, we reach step 4, isolating the derivative. To solve for di over dx, we multiply both sides of the equation by y. This gives us the expression di over dx equals y times the quantity, v of x over u of x times u prime of x, plus v prime of x times log of u of x. To complete the process, you must substitute the original expression of y back into the equation. This ensures that your final answer is written solely in terms of x. We will apply these steps to a concrete example shortly, but before we do, it is important to discuss the critical constraints regarding the domain of these functions. Critical constraints. Now that we have covered the systematic process of logarithmic differentiation, it is crucial to discuss the specific conditions under which this method is actually valid. For this technique to be mathematically sound, there are 2 primary constraints that must be met. First, the overall function f of x must be positive, meaning f of x is greater than 0. Second, the base of the function, which we have denoted as u of x, must also be positive, meaning u of x is greater than 0. The reason for these restrictions is fundamental to the nature of logarithms. As you may recall, the logarithm of 0 or any negative number is undefined within the set of real numbers. Therefore, we must ensure these conditions are satisfied before applying the steps we discussed in the previous slide. With these critical constraints in mind, let us move forward to an illustrative example to see this process in action. Illustrative example. Now that we have discussed the theoretical framework and the necessary constraints, let us apply this knowledge to a concrete example. Please look at slide 4. Our objective here is to find the derivative of the function y equals x to the power of x, as we noted in the introduction. Since both the base and the exponent are variables, we cannot use the standard power rule or exponential rule. Instead, we will follow the systematic process we outlined in the previous slides. Starting with step 1, we take the natural logarithm of both sides of the equation. This gives us the natural log of y equals the natural log of x to the power of x. In step 2, we apply the logarithmic power property that we discussed earlier. By bringing the exponent down as a multiplier, the equation simplifies to the natural log of y equals x times the natural log of x. Now we move to step 3, where we differentiate both sides with respect to x on the left-hand side. We must use the chain rule. Therefore, the derivative of the natural log of y is 1 over y times di over dx. On the right-hand side, since we have the product of two functions of x, we apply the product rule. This results in 1 over y times di over dx equals x times the derivative of the natural log of x, plus the natural log of x times the derivative of x. In step 4, we simplify these derivatives. Since the derivative of the natural log of x is 1 over x, and the derivative of x is simply 1, the equation becomes 1 over y times di over dx equals x times 1 over x, plus the natural log of x times 1. This further simplifies to 1 over y times di over dx equals 1 plus the natural log of x. Moving to step 5, we need to isolate the derivative. To do this, we multiply both sides of the equation by y. This gives us di over dx equals y times the quantity 1 plus the natural log of x. Finally, in step 6, we must express our final answer solely in terms of x. We substitute the original expression for y back into the equation. Since y equals x to the power of x, our final result is di over dx equals x to the power of x times the quantity 1 plus the natural log of x. Please pay close attention to each of these steps, as we will see in the next slide that skipping the chain rule or forgetting the final substitution are very common pitfalls. Common mistakes to avoid. Now that we have walked through the theoretical process and a concrete example, let us examine some common pitfalls. It is important to be aware of these errors to ensure your calculations are accurate. First, be very careful not to apply the power rule incorrectly. A common error is treating x to the power of x as if it were x to the power of a constant n, and incorrectly writing the derivative as x times x to the power of x minus 1. Please remember, as we mentioned in the introduction, the power rule only applies when the exponent is a constant, not a variable. Next, watch out for forgetting the chain rule when differentiating the natural log of y. Many students simply write 1 over y, forgetting that since y is a function of x, you must multiply by the derivative of y with respect to x. This is a crucial part of the implicit differentiation step we performed in our example. Another frequent mistake is neglecting the final multiplication. It is easy to stop your calculation once you have reached the point where 1 over y times the derivative of y with respect to x equals a certain expression. However, your ultimate goal is to isolate the derivative, so you must remember to multiply both sides by y to find the final expression for the derivative of y with respect to x. Finally, do not ignore the domain constraints we discussed in the third slide. Always remember that the base must be positive. If the base is negative or 0, the standard logarithmic method we have learned today cannot be applied directly, as the logarithm of a non-positive number is undefined in the set of real numbers. Keep these warnings in mind as we move toward our final key takeaways. Key takeaways. Now that we have covered the step-by-step process, worked through an example, and identified common pitfalls, let us conclude with the key takeaways to solidify your understanding. First, let's revisit the purpose of this method. As we discussed at the beginning, logarithmic differentiation is specifically used for functions where both the base and the exponent are variables. In general terms, this is when we have y equals u of x raised to the power of v of x. The core logic behind this technique is to simplify the problem. By taking the natural log of both sides, we convert a complex exponentiation problem into a much more manageable multiplication problem. This is made possible by the logarithmic property, which allows us to bring the exponent down, stating that the log of a raised to the power of b is equal to b times the log of a. If we look at the general result of this process, we arrive at a final formula. The derivative of y with respect to x equals y multiplied by the quantity. V of x times u prime of x divided by u of x, plus v prime of x times the log of u of x. This formula is essentially the mathematical summary of the steps we performed in our illustrative example. Finally, always remember the critical requirement we mentioned in the constraint slide. For this method to be valid, both the base and the function itself must be positive. This is a fundamental rule because the logarithm of 0 or a negative number is undefined within the set of real numbers. Keep these points in mind, and you will be able to approach any variable base, variable exponent problem with confidence.